Now I like to use the video to elaborate two particular examples so that once when you get back home, you can revise it much more easily. And the two examples that I like to show, one is a continuous and another one is a discrete one. For most of you, probably discrete type is pretty new to you. So now refer to example C, then example C, that is find the energy for x and is equal to half to a power n. I like to remind you again, for discrete we use this n, for continuous we use xt. Okay, so the brackets are different as well, so make sure from now on you know the difference between the continuous and discrete. Okay. Now, so from the equation, if you remember that the energy is equal to summation from n to a power minus infinitive to positive infinitive, then x and square. Then you may ask why it is from negative infinitive but not from zero, because for some cases the energy, the signal may exist before time is equal to zero. You can simply consider it might be a kind of residual energy, residual things left inside the circuit. Now I'm going to talk about that later on, but in the meantime, you simply consider it as a kind of mathematical issue. Now in this case, right, oh, I missed that someone here. I'm sorry about that. Now, I'd like to talk about this UN. If you still recall that, that is the unit step function. Okay. There's ut. It starts from time is equal to zero. That means anything before time is equal to zero, it doesn't exist. So, if I'm going to say that cosine omega t ut, that means we are going to consider cosine omega t when t is bigger than 0 and t all the way, so we don't consider cosine minus omega t minus 2 omega t. Okay, so for discrete signal, in this case, there is something like that. This is how we draw discrete signal. So discrete signal, there is something like that. The UN, that means we only consider all the signal when n is equal to 0, nothing there, nothing there. Okay, this is what UN is about. Okay. Now because of that, so it means we only have when n is equal to 0, 1, 2, 3. When n is equal to minus 1, minus 2, no such thing. That's what UN. Okay, I'm sorry about that. I missed a UN here. It's supposed to be UN. Okay. Now, because we realize that n doesn't exist when n is less than 0, then we can rewrite it into, right, n is equal to 0, infinitive, then it become half n square, or it becomes summation n is equal to 0 infinitive, right, half 2n, then is equal to ex is equal to, when n is equal to 0, whatever things to power 0 equal to 1. So we've got 1 plus half to the power 2. When n is equal to 2, then we've got half to the power 4 and half to the power 6 and so on. Then we can carry on to rewrite it into 1 plus 1 over 4 plus 1 over 4 to a power square, 1 over 4 to a power 3, and so on. Now, the question is about how we are going to rewrite this particular form into a compact form to give a nice and good numerical answer. How we are going to do that? We have to rely on something like that, right? Suppose just consider this particular thing 1 minus a over 1 or 1 over 1 minus a. You consider this thing, okay? You consider this thing. Then when we consider this guy, I use a long division to work out this guy, to work this one out. Then I've got this one will become 1 minus a minus a square. Then I've got a square. Then I've got a square, and so on, a cube, and a 4, and and so on. Now the good thing is, if a is smaller than 1 is equal to 0.9, 0.8, and something like that, a to the power 10 will become very small, so the whole thing here will converge. But suppose if a is equal to 1, then we have 1 plus 1 plus 1 plus 1 plus 1, then it will tend to infinity. So we can get a numerical answer, or we can get a converged answer when a is less than 1. So in this particular case, we know that a is equal to 1 over 4, that is less than 1. So because of that, then we can come back here. Ex is equal to 1 over 1 minus 1 over 4. Now, mind you that this one is minus 1. Then we will have 1 over 3 over 4. So Ex is equal to 4 over 3. That is the answer. Right. Here we use two major concepts. One major concept is about how we are going to get rid of this un. Get rid of this un in this calculation. We get rid of un, then we remove n equal to minus infinity, we write it into n is equal to 0. That's pretty important because of un. Another very important concept, we make use of this particular case, but provided when a is less than 1, then we can rewrite this particular equation into this compact form. So the next example I'm going to work with you is going back into a continuous case.